Our next application of polynomial method is about the affine hyperplanes in Rn. So what is hyperplane? An affine hyperplane is a set of vectors, let's say H, which is equal to the set of points where A dot x is equal to B for some A and B in Rn. Okay, let me point out that there was a typo. B is not a vector, right? Let me fix it. B is in R, of course. Now, here's the theorem that we're gonna prove. So this is due to Alon and Brady in 1993. So if M affine hyperplanes in Rn avoid 0, the origin, but cover all other 2 to the n minus 1 points in this cube, then M has to be big, has to be at least n. And if it's true, then this is tight. The reason is, you can think of the x1 is 0, x2 is 0, xn is 0. So these are n hyperplanes. Okay, then n affine, oh, not 0, 1. These are n affine hyperplanes, which covers all 2 to the minus 1 points. So therefore, that's an example where you can actually cover them by these hyperplanes avoiding 0. And we can show that this is actually tight. And I'm going to show you a stronger statement. So here's the lemma. So let P be a polynomial. Okay, in n variables, let's say x1 of xn, with the value at the 0 is non-zero. Okay, if px1, x2, xn is equal to 0 for all x1, x2, xn, which is in 0, 1 to the n minus this origin, then the degree of P is at least n. Now, if we assume this lemma, then we can prove the Alon-Brady's theorem. Prove of Alon-Brady assuming this lemma. Let H1, H2, Hm be the affine hyperplanes covering all of them except the origin. Let Ai, Bi be the vector such that Hi is equal to the set of points in Rn such that Ai dot x is equal to Bi. Alright, now define P of x to be equal to, so P of x, this is polynomial, P of x 1 of the xn is equal to the product of Ai dot x minus Bi. All right, and this is a polynomial of degree m. And what's the property? When you put x to be 0, then this becomes non-zero. And if x is non-zero vector in the cube, this is going to be 0 by the assumption, because these hyperplanes cover all the points except the 0. So the p, then the degree of p has to be at least m, at least n. So this lemma is essentially implying the theorem. So how do we prove the lemma? Suppose not. Now we're going to define f of x1, x2, xn be the p of x1 up to xn minus some constant times product of xi minus 1, where c is chosen so that f of 0, 0, 0 is 0. We can choose that because when xi's are 0, then this number is non-zero, so we can choose c to be some number so that this, well, that number will, but this divided by that when xi's are 0. And this is non-zero. And c is non-zero, right? So this means that the coefficients of the product of xi in f is c, which is non-zero. This is because the degree of this is less than n, because we are assuming that m is less than n, and this is the degree m, and m is less than n, so you never have a term like this over here. So the coefficient is non-zero, so therefore there exists xi in 0, 1 up to the n such that f of x1, x2, xn is non-zero. But that's a contradiction, because when xi's are not the 0 vectors, then this is going to be 0, that's going to be 0. If this is 0 vector, then this is 0 by assumption, right? So that's contradiction. So this is by the combinatorial new strand. And that's a contradiction. All right.